Okay, so now let's try to solve the problem we just formulated. And our goal will be to find the second best optimal solution. So to just a review, first best means when you have complete information, the best policy to do. And the second best is under information asymmetry, what's the best pricing plan for you to offer. Okay, so now we will introduce the standard way for solving this standard two-type problem. Sometimes you will see some variants of this problem, but in many cases, the following standard way will be able to solve, or at least greatly reduce, the complexity of the problem. So please pay attention to the following analysis. The key is that we want to analytically solve the problem. Only with analytical solutions we may generate general insights. Okay, so we're going to do that. Oh, by the way, so just a review: IC constraints, IR constraints, and the objective function. The term analytical solution basically means I want to know in my optimal solution how these four decision variables are the functions of parameters. Here, parameters include beta, c, theta h, and theta l. Okay, I want to express my decision variables as the functions of parameters. So the first observation we may get is to add the two IC constraints together. So this is ICH and this is ICL. If we add them together, I'm going to cancel these four t variables, right? And then I will only get this as the sum of these two terms, which will be greater than or equal to the sum of the other two terms. Then we do some arrangements. Let me put the two terms with VQH together. So I'm going to take this term to the left hand side. I can get something like this. And similarly, I will get something like that in the right hand side. Because theta h minus theta l is positive, I can remove them. And then I can get something like this. V of QH will be greater than or equal to V of QL. And then, because V is increasing, okay, because V is an increasing function, so if QH is greater than, if V of QH is greater than V of QL, then I immediately know QH is greater than QL. Okay, so that's some results I may get. This result is called the monotonicity condition. It says that if a plan is incentive compatible, then the high type consumer will consume more, or in the optimal plan, we should offer more consumption to the high type consumer. Okay? Because this condition comes from these two constraints. If a solution is feasible, it must satisfy this condition. So that's something we are talking about. If we want to induce the two players or the two types of agents to tell the truth, then QH must somewhat be greater than QL. Okay? There must be an intuition like this, right? The intuition is simple. High type consumers basically prefer the high consumption because they are willing to, they get more, they get higher utility when they get a higher consumption. So if we want them to prefer the contract intended for them, QH should be greater than or equal to QL. Okay, so that's the first insight we may get. Now, consider the following. I can combine ICH and IRL to imply that one of the constraints IRH is redundant. So what's that? First, we can see that my ICH constraint says this. Okay, the high type consumer should prefer the high contract to the low contract. And then from here to here, it's simply an application about theta h is greater than theta L. Okay, V is positive, so theta h is greater than theta L. And then the right hand side, this term is exactly the left hand side of IRL, because the low type consumer should get at least 0. Okay, so combining this, we know that IRH must be redundant. If I can satisfy ICH and IRL, I can satisfy IRH. Okay, so that means in my program, IRH is useless and I can take it away. It must be satisfied. The intuition is that the high type consumer will earn a positive rent or a positive utility. And immediately we know, as a manufacturer or as a seller, I now cannot extract everything from the agent. The agent will be able to get at least something. Okay? I haven't really solved this problem, but through my analysis, I can know this. So now I have 3 constraints left. Now I'm going to guess that ICL will be redundant for a while. Okay? So I haven't proved that ICL should be redundant, but now I am guessing that it will be redundant or it will be satisfied. So what does that mean? I think the low type consumers does not have any incentive to pretend to be a high type. Okay? If you ask a consumer and if he really hates your product, there's no reason for him to say your product is good. I'm going to pay you a lot of money. That's impossible. So we have this intuition, and that intuition guides us to assume that ICL should be redundant for a while. I'm going to ignore or relax ICL, and later when I get an optimal solution, I will check whether that constraint is really satisfied. So this strategy is familiar, right? When we have a constraint optimization problem, we may relax some constraints and then try to get an optimal solution. If that optimal solution really satisfies all those relaxed constraints, then we're done. So I'm going to play the same trick here. After that, I only have 2 constraints left. With these 2 constraints, I'm going to claim that both constraints must be binding at any optimal solution. So again, binding means that constraint must be equality at this optimal solution. So let's see why. Consider the first constraint. The first constraint has TH there. As a seller, I want TH to be as high as possible. So I will keep increasing TH until I cannot do so, which means until TH is bounded by ICH. Okay, I will keep increasing TH until the constraint is binding. If the constraint is not binding, I definitely can choose to increase TH to earn more. So ICH must be binding. At the same time, IRL must also be binding. So for IRL, I have TL here. I will try to increase TL until the second constraint is binding. You probably want to ask, TL is also here, right? That's a good observation, but here, TL is at the right hand side of ICH. When I increase TL, that simply relax this constraint instead of making it tighter. So when I increase TL, I will never violate ICH. So it doesn't matter. I can keep increasing TL without considering ICH until I hit the boundary of IRL. So I know both of the constraints will be binding, and you probably want to verify this. If we did not ignore ICL, the constraint that we ignored in the previous slides, then we cannot claim that IRL will be binding because TL will also appear here. then we can only say either this one or that one will be binding. Then things will become more complicated. But with the previous observation, now things go smoothly. So now the problem really becomes this one. One objective function, two equality constraints. When we have an equality constraint, that just means we can remove one variable, because once I know, for example, QL, I know what's the value of TL and so on. Okay, so I'm going to replace TL by theta L VQL, and then I'm going to replace TH by this and this. Okay, so that's my idea. So I know in an optimal solution, TL and TH must be blah 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 blah, blah expressed in this way. And then after that, I will get an unconstrained problem like this. TL is replaced by this term, and TH is replaced by these three terms. This is my unconstrained problem. In the next video, I will complete the solution process for solving this problem and then discuss the insights. Thank you.